We've been talking a lot about velocity and acceleration, and especially with respect to acceleration, we've talked about speeding up, slowing down, and turning, but we really haven't talked in detail about turning. And so that's what we want to do now, is we want to focus in on how you accelerate, how much you accelerate while you're actually turning. So imagine that you're traveling around in a circle at a constant speed. So that's what's meant by uniform circular motion, traveling along a circular path at a constant speed. So in the figure over here, we can see a car at 3 different positions as it's moving around the circle. We can see the velocity is tangent to the circle, since again the velocity is always tangent to the path that's being followed. If this car is turning, though, we know that it's going to be accelerating in the direction of the turn, perpendicular to the velocity. So that means it's going to be accelerating toward the center of the circle. So whenever you're traveling at a constant speed along a circular path, you're always accelerating toward the center of the circle, and that's known as centripetal acceleration. So centripetal is an adjective which means toward the center. What we want to do now, though, is we want to try to figure out exactly how much acceleration an object would have if it's traveling along a certain circle. If I told you something was speeding up at 5 meters per second squared, by now you should have a good sense of exactly what that means. Or if something is slowing down at 2 meters per second squared, you should have a good sense of that. But now we want to figure out what it would mean to say, for example, accelerate at 8 meters per second squared while you're turning. We want to be able to put a number to the acceleration. So let's think a little bit about this. As this car is moving around the circle, as it moves from the top of the circle to the bottom of the circle, notice that the velocity completely reverses direction. So that's a very large change of velocity. So let's think about how quickly that change is going to occur. So for example, if you were traveling at a given speed on a big circle or a small circle, how that would affect how rapidly your velocity is changing. So if you're traveling along a big circle at a given speed, it would take you a relatively long time to get from the top to the bottom of the circle. So your velocity would reverse and change in a large amount of time. On the other hand, if you were traveling around a smaller circle at the very same speed, then it would take a lot less time to get from the top to the bottom. Your velocity would change by the same amount as it reverses, but it would do so in a lot less time. So that's more acceleration. So smaller circles involve more acceleration because your velocity, for example, reverses in less time. But even for a given size circle, think about what would happen if you were going faster or slower. If you were going faster, you're going to get from the top to the bottom of the circle in less time, which means your velocity has to change more rapidly, and so that also gives you more acceleration. In fact, if you're going faster, your velocity is bigger in the first place, so it changes by a larger amount and in less time, so that gives you an especially large acceleration in that case. So those are the 2 factors that go into determining the actual amount of acceleration when you're turning. It depends on the speed. Faster speeds, more acceleration, and it also depends on the radius of the turn. A smaller radius involves more acceleration. In fact, it's the speed squared divided by the radius of the turn. So we could write it as an equation in this fashion. Now, as far as units go, the official unit for measuring speed would be meters per second. So in the numerator, we'd have v squared, which would give us meters squared per second squared. Then we have to divide that by the radius, and the official unit for measuring the radius would be meters. So if we have meters squared per second squared and then divide by meters, that gives us meters per second squared. And that's the unit we've been using all along for measuring acceleration. So just like any of the other equations we've dealt with, if you put official units in, you'll get official units out. If the speed is in meters per second and the radius of the turn is in meters, you'll get the acceleration in standard units of meters per second squared. Now that's very nice for driving around in a circle, but it's not likely if you're driving your car that you actually drive around in circles very often. Fortunately, this formula applies to much more than just actually traveling literally around in a circle. So let's take a look at another possibility. Here is an overhead view of a path that might be followed by a car. So maybe this shows the road that your car is driving along. So imagine we start at the left end and we go around the first turn, turning to our right. And then as you hit the second turn, heading downward, you would turn to the left and go around the second curve and then finish out on the far right-hand side of the path. So as you're driving along this particular road, you actually turn twice. And even though you never actually literally move in a circle, every time you turn, anytime an object turns, it's moving along at least part of a circle while it's turning. So here's a look at those two circles. So as you make that first right-hand turn, you're actually traveling along at least part of that red circle as you make your turn. And then as you make the second turn, the left-hand turn, as you're heading down and eventually heading out to the right in the figure, you're traveling for part of the time along the green circle. And it turns out the radius of those circles is the radius you would use for finding the centripetal acceleration. So there is the large radius for that red circle. So that first turn involves a large radius turn. And the second turn, where you're traveling along part of the green circle, that's a much smaller radius circle. So that's a smaller radius turn. And so if you think about the formula, the smaller the radius, the bigger the acceleration. So basically, the more sharply you turn, the smaller the radius and the larger the acceleration. So that radius in the formula basically indicates how sharp the turn is. And hopefully that agrees with your own personal experience. Whenever you have been driving and you make a turn, the more sharply you turn, the more exciting or the more alarming it is. The physical sensation you get while making that turn is the acceleration. You're feeling the acceleration of the turn, and there's certainly a lot more physical sensation that goes along with sharp turns than gradual turns. In fact, v squared over r is the correct value for the acceleration even if you are speeding up or slowing down. If you're speeding up or slowing down, then there'll also be acceleration parallel to the velocity, which involves the change of speed. But the part of your acceleration that's toward the center of the circle will still be v squared over r, even if you're changing speed as you make the turn. So put in your speed at any given moment, square it, divided by the radius. That's how much you're accelerating toward the center as you turn.